Thank you, Florent and Lenka and the rest of organizers, Gabrielle, for having me here. It's very nice. Some of the familiar faces I see. And yeah, so first, this is a work that I did with many collaborators. Some of them are actually in this room, and I'll try to acknowledge them as slides go. Okay, so today is really about a story that basically connects, something that might be a bit, sexy, and you might, that might be related with lots of hype, and something try to relate it with maybe problems and situations that are maybe a bit more grounded in some areas of classic, let's say, statistics and even computational theory. So, but I mean, since there are neural networks in the title, I have to start with a deep learning slide. And so we have all seen, a kind of very impressive and successful applications of these models that not only, now we help us to sort of transfer from Van Gogh to Munch and stuff like that, and do very like superhuman object localization and segmentation. These things are also now used in robotics with a relatively good success, even in like medical imaging, for like pre-screening of some cancer problems, machine translation, speech recognition. So we really see that, okay, now it's a consensus, this thing works, right? There's really something there. And so, and now the question is, well, what is really at the core? What is really the reason why these things work well? I mean, of course, this is a question that is kind of the holy grail of people who try to understand the foundations of deep learning. But maybe we can start by trying to identify what do these problems all have in common. Okay, and these problems, they have in common that they are really the signals, the data that we are feeding to these models lives into a very specific, regular structure. In particular, images are defined on a grid, sequences are defined on basically on a one-dimensional grid, etc. And the models that really work well, they leverage this structure by basically enforcing that it's not just a generic neural network, it's a convolutional neural network, right? We really have a lot of structure there that really changes the behavior. So what is really this geometric structure that these GNNs are capturing? And maybe how can we take this lesson and use it in other problems that might also have geometric structure, but does not appear in this very nice regular way? Okay, so that's the kind of the topic of today's lecture. So what do I mean by going beyond regular grids? So one can think about problems that involve objects like that, right? So you can model, let's say, a surface as a manifold, right? So a manifold has geometry, but it's non-Euclidean, right? You have things that have curvature that is not necessarily uniform. You can also think about problems that involve, let's say, a social network, right? I mean, here we have we have some representatives, myself also as a visitor, of why would one care about doing learning on this kind of objects? So, and in these problems, we have actually also a variety of different flavors, right? So there might be problems in which what we care about is the domain itself, right? So we will see some examples later in the talk where I don't really have a signal as I had with images, right? I just have a domain and I want to learn something, I want to understand something about this domain. But there might be other problems where I have both things, right? I have the domain and I have data on the domain. For example, in a social network, I might be, or in a Twitter, I might be interested in understanding, some statistics about the signals that propagate in this network. You might have problems in which the domain is always the same, is fixed, right? So again, if you are Facebook, you have a social network, that's one network, and then you have, the variability in the problem comes from basically changing the data. But there might be other problems, like for example, if you want to do geometry, where every time you have a new data point, you have a new domain, right? There's some geometry that basically is varying at every data point. And you might even have examples where the graph is given, is observed by us, or problems where the graph is not even known. Okay, so we will see also some instances of this, for example, in particle physics, or in some problems where the only thing we can measure is just a cloud of points, right, in some Euclidean space. We believe that there might be some structure between these points, but we don't know. Okay, so we don't know the graph. And so in all these problems, we want to understand how can we leverage, or how can we basically use or exploit the geometry on these problems to actually get as much performance, as better performance as we can. And so one of the main topics that I will talk about, yes, maybe that's a false connection. Okay, so one of the main applications that I will focus on today is basically try to understand how can we is it possible to use these ideas to study problems that are maybe belonging to, let's say, the classic fields of maybe computation and statistics? For example, problems that really ask the question, how hard is to solve an inference problem? Okay, so one very representative example that we will cover is what's called the community detection problem, right? So I observe a graph. In that case, it's a very nicely colored graph that everyone can see here that there are two communities, right? So the question is, I only observe the graph. So I don't give you the colors, and I don't give you this super nice embedding that already shows you the things as this. The question is, how can we identify this planted community structure by observing this graph? So it turns out that this question has both a motivation in practice. You might be interested in solving this question, but it's also a very profound question that involves statistics and computation. And so in particular, questions like, when can this problem be solved by any means? In particular, if I just do it maximum likelihood, when is the maximum likelihood guaranteed to succeed? And this will be a question that depends on essentially a notion of signal to noise of the problem. And then the other question is, when can this problem be solved efficiently with a polynomial time algorithm? So in this context, what we all try to understand is how can learning enter in this picture, right? So this is like a research program in which, by the way, Florent and Lenka here are one of the prominent researchers pushing this program. How can learning enter this game, right? And we'll see some instances of maybe exploiting the geometry of these problems to actually use machine learning in a principled way. Okay, but let's start with the things that we know work well. That is, how can we do, let's say, geometric deep learning on data that lives in a nice Euclidean domain. Okay, so now the data points in the classification problem are functions in a domain that is, you can think about this domain as being just a grid or like a two-dimensional or one-dimensional grid. So in many of the problems in supervised learning can be seen as essentially solving an interpolation problem in this super high-dimensional space, right? Where I need to discover a function that maps functions from this domain to some output space that might contain labels or might contain locations. And so the only thing I know about this function, the only thing I observe about this function is the value of this function in some point, right? The training set. So of course, I mean, this problem without anything else doesn't make any sense, right? It's not well defined because I need to give assumptions on what is the class of functions that I need to approximate, right? So that's the main question, like the starting point should be, what do we know about this function before we try to interpolate it? And so in the case of images, one particular source of variability that might be important, that might help us to understand what kind of assumptions are we actually indirectly encoding into these models, is this notion of what I call this geometric noise, right, or geometric stability. So you can think about it as the effect of, when I add noise to an image, typically what I do is that I add that noise to the pixel values, right, to the RGB colors. I just change the RGB values. So here, what I'm going to do is I'm going to add noise to the pixel locations. I'm going to move the pixels around, right? And so that's what this change of variables, or if you want, this diffeomorphism is trying to do. So when you start moving the pixels around, right, that's the sort of variability that, in the first order, you can accomplish, right? You can basically model mathematically this kind of, geometric transformations. And so because we are adding noise, we need to quantify how much noise we are adding, right? And so one particular way one can quantify how much noise I add is how much I am going to distort the domain, right? So, and so one way where one can measure it is basically by looking at basically how much the domain is stretched in a uniform sense. And so with this kind of variability, we can model many things that happen in the low level, right? The image acquisition, we can model, the effect of changing the point of view, of looking at the same thing but from a different angle. We can model, many transpositions in speech recognition, et cetera, et cetera, et cetera. So the question is, well, if we believe this assumption, right, that if I add this amount of noise to my input, the function that I want to interpolate is going to change very little, how can I leverage this kind of prior in a machine learning model? So it's probably not a surprise that one particular way to nail, to adapt well to this form of noise is to actually use this famous, by now, architecture that essentially does one very simple thing many times, right? And the simple thing that it does is basically a convolution with a localized, right? And here it's like a really bold. Basically, it's a filter bank with localized filters that are interleaved with these pointwise activation functions. Okay, and so this thing is repeated, these weights are trained, and I guess that everyone here by now understands very well this architecture, right? So I don't need to really go into the details. So why is this architecture well designed, plays well with this geometric noise? So it's not the topic of today's talk, but just as a kind of a hand-wavy argument, one can see that basically the fact that these linear operators from the previous slide are convolutional plays very well with this idea that basically the function that I want to interpolate is essentially invariant to translations, right? If I have a rigid, if I add no noise, basically a rigid translation corresponds to adding no noise, right? It's just a rigid thing. So one way to leverage this invariant is to use convolutions, and it's localized because really what we want is to be geometric, to be stable with respect to small like things that are local translations, right? And the fact that you can see this intuitively is that if I convolve my image with a large filter, right? Anything that happens within the support of the filter is going to be very unstable. It's going to react to anything that doesn't look like a translation within the support of the filter. So if I have filters that have small support, then if the filter, the only thing it sees is locally like a translation, it's going to basically play well. So this kind of hand-wavy argument, you can formalize it, and actually this is what Stefan did in his first paper on scattering, that basically you can prove that essentially this way of extracting information with this very particular localization in time and frequency is the thing that really plays well with this geometric deformation model. But of course, stability is only one part, right? As you all know, I mean, it's very simple to define a representation that is stable, right? I just map everything to 0. I map everything to, to whatever you want, right? But of course, I mean, the mystery and in a sense the big open major open theoretical question that is not addressed with this story of stability is how come these models can be stable while being so rich, right? Being able to capture so much expressive information. So this is for another day. Okay, but now the question is, now we want to move, right? We want to move from this Euclidean domain to a more general domain, right? So in a sense, we change our functional space from being a functional space over a Euclidean domain to a functional space over a generic domain, right? And we can model generic metric domains with a graph. We'll see later a bit more details. Okay, so now the idea is that we want to basically be able to build geometric stability with respect to a non-Euclidean domain. So what does this mean? Okay, so in the case of Euclidean images, I could basically show you what we mean by this geometric stability. What does it mean in general? So we can start with basically models that are undirected. So for the rest of the talk, I'm just going to focus on undirected graphs. And basically, the similarity of the problem is encoded in this similarity matrix. So if first we assume that this graph can be embedded basically in a low-dimensional space. So think about the first example where my graph is just modeling, let's say, the particles in a accelerometer. In the particle accelerator, I have particles that are basically measured in, like, say, 3-4-dimensional space. So just think about a graph modeled that is embedded in this low-dimensional space. So in that case, we can basically use the extrinsic information. So when I say extrinsic, is basically a model that is relying on the embedded space, right? On the ambient space in which the graph is embedded. So if I'm allowed to use extrinsic information, then the question is pretty easy, right? Because in particular, if I have a deformation field on the extrinsic domain that is Euclidean, I can infuse it, I can bring it into a deformation of the graph, right? That this is very natural to think if I have a graph that lives in, let's say, in this slide, in 2D, what does it mean to deform the graph? Well, so if I have a deformation on the plane, I just infuse it, I just completely apply it into the graph. That's pretty simple, right? And in a sense, this is a model that is already pretty good in many problems, right? In problems where I'm allowed to use this kind of low-dimensional embedding. So in particular, if I am interested in surfaces, we'll see later, this is one model, one prior that is pretty good. But of course, we are not very happy, right? Because this is still relying on the fact that I can have this low-dimensional embedding of the graph. And we know people, especially here who are more on the theory side, this is a bit limiting as an assumption, right? There are many examples that we want to solve where we cannot do that. So can we think about this problem in a more intrinsic way? You have a question? Yes?
Why does it need to be low-dimensional?
Yeah, because if it's high-dimensional, it's like you are cheating, right? You have no good way to control, let's say, these metrics of the diffeomorphism that I defined. If you want to define them in high-dimensional space, you might be exposed to problems of how do these metrics of diffeomorphism scale in high dimensions. Maybe, but I'm scared to go in that direction. Well, yeah, okay. So there's another way where one can look at the problem. I try to basically make it a bit more, let's say, abstract, a bit more intrinsic. So one way where we can think about the deformorphism, I define it as a deformation. I define it as something that acts on the signals, right? I take an image and I deform it. But one can think about the deformorphism as something that is acting on the domain itself. It's a change of variables, right? So if you remember from, like a stupid, like very simple change of variables, when I apply a change of variables, in a sense, what I'm doing, I'm changing the metric, right? I'm just, I can apply the change of variables, and essentially what I'm doing is essentially changing the metric of the domain, right? And if you can see that basically the cost in this example, having a small change of metric is equivalent, as I described before, as having a small deformation, right? Basically the thing that dominates this term in the first order is basically the norm of the Jacobian. And so one can argue that now maybe what we want is to have a representation that lives in a domain, that the representation, if I change the domain, if I change the metric of the domain a little bit, I want the representation to be stable, right? So the only thing I care about is having a notion of basically what does it mean to change the metric a little bit? Okay, so that's the question that we are going to describe. So one way where one can define basically a metric on a general graph is to use, so this is, of course, by all means not the only option, is to use what we call this diffusion distance. And this is a very natural distance, right? So let's say that I have a graph. So in a graph, what I can do, I can model some basically a diffusion process that is essentially following a particle as it moves in the graph. And I can define basically a distance between 2 points in the graph as basically if I initialize my diffusion process at x for a certain time t, and if I initialize my diffusion process at point y at time t, how do these distributions look like, right? If the distributions look very close to each other, maybe I can just use this to define a distance between the 2 points, okay? So this is called a diffusion distance, and this is basically a very beautiful work pioneered by Rafi Kaufman, and many others, and Wasnader, and Mauro Maggioni, etc. And so this, we can use it to define basically a distance, like a metric distance between two graphs, right? And so you can think it as basically how can I basically permute the nodes of one graph with respect to the other in a way that when I apply the diffusion in one graph and I apply the diffusion in the other graph, the diffusion operators look similar, okay? And so this, for those of you in the audience who are familiar with this story, this is basically a kind of a stronger version of the Gromov-Hausdorff distance, right? So basically this here, I'm optimizing not only for pairs of x and y, but for all possible vectors, right? Not just the vectors that look like a difference of Dirac's. And so here, again, it's defined for simplicity, assuming that the two graphs have the same number of nodes. But again, as the experts in the room that have experience with optimal transport, this is very standard to generalize it to different size using couplings. Okay, so that's one way. And then with this, we can state our geometric stability property in general, right? So what we want is that now, if I have basically a representation of signals on a graph, what I would like is that if someone, like someone exterior, perturbs the graph in a way with a small deformation, the representation should not change. And this should be uniform with respect to basically to the signals on the graph. Okay, so it's basically a way to generalize the notion of geometric deformation to general domains. And here, for the rest of the talk, so I define here a representation of basically that takes as input both the graph and the signal. It might be in some applications, you will see the only thing we care about is the graph itself. Right, so in that case, we just basically we need to marginalize over the signals. So either we can just use as a signal some deterministic function of the graph, or we can marginalize with respect to some distribution. Okay? So the question, of course, is how can we construct representations that satisfy this property? Okay, the same way as confnets are good to play well with the deformation in images, how can now we construct a representation that plays well with this notion of deformation? So maybe we can look again at how the confnet can be basically expressed or can be thought in a more general domain. Okay, so in a sense, we need to abstract the fact that the confnet lives in a grid, right? We need to abstract this thing. So we can think about we can look at basically the confnet, this operation on the formula. Before there was a convolution here, right? So a convolution, in a sense, you can see it as a linear in the case that, as I told you, right? The filters are localized in space. So you can think about every possible filter that can be written in every layer of the ConvNet. You can see it as being basically a linear combination of kind of generators, right? So think about what can you express with local operators that are convolutional. So basically, you can express local derivatives, right? You can take the derivative with respect to the horizontal, derivative the diagonal, horizontal, whatever. Okay, so you can think about, if you give me the domain, from the domain I can define this family of, in that case, like differential operators, that, and then the model, what I learn, is linear combinations of these operators, okay? So now the question is, how can we use this story for a general graph? So in other words, if you give me a graph, how can you give me this family of operators that basically that satisfy this property of locality, okay, and that basically are essentially that can be applied in any position of the domain. So in a general graph, we don't have directional derivatives, right? It doesn't make any sense to take the derivative with respect to the horizontal or diagonal direction, but we have operators, okay? We have operators on the graph. We know, in particular, how to compute the low-pass filter, right? So if you give me a signal on a graph, I multiply it with the adjacency matrix. What I get is I replace every point by a local average of its neighbors. So I'm basically computing a low-pass filter, okay? And by definition, essentially, the low-pass filter is stable. Right? This is basically just applying our definition of stability. And so it turns out that, again, Gabriel here might know it, right? Is that once you have a low-pass filter, you have everything, right? You can construct high-pass filters very easily. You just need to remove the low-pass filter from the signal, right? You have a high-pass filter. So basically, this idea, you can plug it without much effort. And to show that once you have a low-pass filter on a graph, essentially you also have a family, you have a high-pass filter. And then this high-pass filter, in the case, again, using diffusion, you can also show that it's also stable to deformation. Okay, so essentially, now in a graph, we have a low-pass filter and a high-pass filter, that both are local and both are stable. So the same way that in a ConvNet, we basically take these two operators and construct powerful models by learning linear combinations cascaded with nonlinearity. Here we are going to do the same, right? But except that now, instead of having directional derivatives, we just have a high pass and a low pass, essentially. Okay, so this is what graph neural networks are about. So this is a model where every layer is constructed by learning basically a coefficient of a polynomial that is going to mix the low pass, basically the information from the previous layer, once I multiply it with, here in a sense, an all-pass filter and a low-pass filter. And this model was originated already many years ago by Marco Gori and some of his colleagues, and was a bit like underground. It stayed a bit under the radar. It basically went through this revolution in 2012, kind of undetected, but then it kind of resurfaced through various series of works, like a few years ago, and was basically rewritten in a way that looks very close to what I'm showing here. And of course, the same way as ConvNets, you can put all the bells and whistles you want, right? You can do residual layers, you can do gating, you can do you name it, right? So there's everything that works well, batch normalization, everything that works well in the ConvNets, you plug it here, and it tends to work well as well. And of course, you can, this is something that we did some years ago. We can actually reinterpret these models in terms of basically trying to, in terms of like a computational harmonic analysis, right? You can basically relate this to basically doing a harmonic analysis on the graph by just rewriting the family of filters in terms of a low pass and a high pass. And the high pass, in that case, is just a Laplacian operator, right? And so this is something that we did some years ago. We actually, when we did it in a sense the wrong way, right? We tried to learn the filters in the spectral domain, and that proved to be not a very good idea because it was computationally very expensive, right? So now we kind of understood, and now everyone is learning the filters in space as it should be, right?
So here
yes.
is a neural net that takes a signal on a fixed graph, or does it take an input graph?
It can take, the graph can vary. So because you learn implicit, you just learn coefficients of intrinsic operators. So if you change the graph, the family of operators is going to change, but you can still leverage what you learn. You can still transfer from any graph to another, which is not the case if you rely on the full spectrum, right? Because as you know, the full spectrum is unstable.
But
yes?
How do you change the generators of the graph changes?
No. So the graph changes, but you can still define the diffusion. So even if your graph changes, the diffusion is the same. And so one of the limitations that you might wonder, right, is that, well, in the Euclidean domain, I have directional derivatives, right? And it makes a lot of sense to have a filter that is sensitive to this direction and a filter that is sensitive to this direction. Here, the underlying high-frequency information is captured with the Laplacian. And the Laplacian, as you know, is an operator that is isotropic, right? It doesn't see the orientation. So this is a limitation that has been interestingly addressed and kind of mitigated to some extent with a number of different extensions that you can build on this basic model. Okay, so in particular, there's a nice family of models, some of them developed by people in DeepMind. So this is a DeepMind paper, this is a Google Brain paper, and many others that essentially try to build up on this by not just learning information that lives on the nodes of the graph, but also information that lives on the edges of the graph, right? And with the hope that maybe the hidden features that you learn on every edge and carry some kind of orientation, like some kind of generalized orientation of what this is happening. But this is, of course, a bit unclear, right? There's no, I mean, this is an intrinsic problem, right? In a general graph, I cannot define global orientation, right? I could only do that if I embed it in extrinsic space and then use the orientation of the extrinsic space in the graph, right? But in general, this is not I don't have enough mathematical substance, right? I don't have enough structure to define this. But there's an example. There's an exception. Okay, an exception is to the problem of representing a surface. Okay, so and here by a surface I mean a 2D surface living in a 3D domain. Okay, and so one way where one can see what's wrong is that the Laplacian is a differential operator, but is second order, right? So the Laplacian, in a sense, is the gradient composed with its adjoint, right? The divergence. So in a sense, it would be great if you could take the square root of the Laplacian, right? In a sense, the Laplacian is a sort of a second-order operator. You can think it as basically a differential operator times the same differential operator adjoint. The problem is that, of course, we don't have a very natural way to compute a square root in general. But in the case of a surface, right, of a surface mesh, it turns out that we can use basically a tool from quantum mechanics that is called a Dirac operator, which is essentially a proper square root of the Laplacian. And the price to pay is that this square root is living in beyond the complex numbers, is the quaternion numbers, which are like these four-dimensional complex numbers. But in a sense, what this square root provides us is it gives us a notion of like generalized orientation in this mesh. And this is something that Ilya, my student, is going to present at TVPR as an oral. And just to give you some example, we applied this problem into the basically prediction of temporal dynamics, right? So what does it mean? We constructed a data set of basically body parts. It's a bit gore, I know, but that's the only thing we could use like for free. So we take body parts and we throw them into the floor by modeling basically, I mean, we didn't do it physically. We just use, of course, a physical model to simulate that. So that's like kind of the ground truth. And you can see it's like a very nonlinear dynamical system. And what we try to do is that now use these neural networks to try to predict the position, the location of this mesh into the future. And we use basically different generators. Okay, and so this would be the model that does not see at all the geometry, just tries to predict every particle independently of the rest. As you can imagine, should not work very well. It does not work very well. And then you can use basically different models of basically different neural network models. So this is a model that is basically only treating the input as a point cloud. So it's just basically discarding the fact that there's basically a local geometry that might be important in the dynamics, just treating everything as basically as a set of points. And this is basically using the Laplacian, and this is the Dirac. And well, it might not be very easy to see here, but if you look at basically quantitative results, these two models work much, much better than these ones, as one would expect. And this model works better than this one, but not spectacularly better. Okay, but still, it works better with the same number of parameters, which is kind of nice here. Yes?
Experiments you can do to quantitatively see the behavior of this rotation of this rotational aspect in the sense of what the Dirac actually gains to.
So you can look at the places where the two models differ. So that's something that we did. And typically what you see is that there are areas where there's like a lot of directional information, like for example in the tip of the fingers and in tips of like this, that Dirac tends to be much better at understanding that, that it needs to basically propagate information, being very aware of the orientation in the direction in which it comes. And then, I mean, again, because here we are in kind of in extrinsic world, it's relatively easy to come up with these certificates of stability, right? And this is a slide. I mean, this theorem has a lot of verbatim, but the take-home message here is that if I use as a generator, I told you that these models are defined through a family of generators. So if I change the graph, the generators are going to change, as Martin pointed out. But if the generators are stable, in the sense that when I change the two graphs, the generators are close, then the resulting representations are also going to be close. Okay, and this is what this result essentially tells us, right? That if the operators are stable, then the resulting neural network is going to be stable. Anyway, so now I'm going to move to other applications. So this is another area where we applied this model. So this is the setup here is particle physics, right? So this is meant to show you an illustration of like a collision in the Atlas detector. And this is basically a detector in the Antarctica. This is a real detector. Here is the Tour Eiffel, very small. And so this is like a huge chunk of ice. And it's meant to detect the neutrinos that are coming from the outer galaxy. And so, and this is a problem where so far we train these models with simulated data, right? So physicists, are interested in trying to understand some questions about, maybe in here quantum field theory, and here they want to understand properties of basically the neutrinos. And so they construct these basically simulation data sets based on their assumptions, and then we try to basically come up with models that kind of invert the generative process, right? Basically to solve a discriminative task. And so here I'm just going to show you like very briefly some of the results that my student Nicolas Coma is getting at NYU. And so what we see here, obviously it's not a surprise, is that if you compare these models that are, they can be plugged very well with technology, like Adam, SGD, we can run these things on PyTorch. So, because we have a very good infrastructure to train these models, and they have essentially the right expressive power and the right stability, we can do like significantly better than the baseline models that physicists have been developing for many years that, of course, are still based on decision trees, with very small amount of degrees of freedom. And so, so these are actually, very promising results, and we are working now with people at also Lawrence Berkeley Lab to try to basically push this technology further. Another example where we apply the same kind of mindset that might look very far from the previous is the problem of few-shot learning. Okay, so for those of you who are not familiar, few-shot learning is this setup where instead of having basically a classification problem where I have few labels and lots of examples for every label, now I'm going to basically flip the thing, right? So I'm going to have a classification problem where basically every new instance, every new point in the data set is going to contain new labels that I've never seen before. Okay? And what I need to learn is not basically how to map images to labels, but it's more how to relate images to each other so that I can find associations, right? So basically here, if I look at this, you can pretty easily tell that this image and this image have the same label, whatever it is, right? I don't even need to know that this is a segue, right? So this model is really trying to learn relations between inputs. So relations between inputs is another way to think about in terms of graphs, right? The graph is a good way to model relationship between things. And so indeed, if you use a GNN, like a graph neural network here, this is an instance where the graph is not known. So basically, the model learns the graph. We got the state-of-the-art results like as of 3-4 months ago. So of course now this is a hot topic. So of course now our model is like it's not state-of-the-art anymore, but that's life. Okay, so now I'm going to basically spend the last 20 minutes of the talk focusing on a kind of on a different story, or like not a completely different story, but yet another example, an instance where we can leverage this story about geometric stability. And these are basically a family of inverse problems on graphs. And so this is just an example that illustrates what I want to say. Okay, so this is a problem, as I said before, of finding the two communities in a graph. Okay, so basically trying to cut the graph into chunks in a way that each chunk is kind of homogeneous, right? So if I show you the adjacency matrix after I've done this coloring, well, it looks right? It looks that in this chunk I have like a lot of connectivity. Across different chunks I have very little connectivity, so it looks about right. But of course, Now I'm going to hide you the color, right? I'm going to show you this. And here, of course, I'm giving you the right order of things, but this is what you see, right? So basically, the problem is mapping from this random matrix, if you want, like this, like a binary adjacency matrix, figuring out that here there's two communities. Okay, and so this is like an inverse problem. And you can actually model and study it in terms of a generative model, right? So rather than, because I need to define like a ground truth for these inverse problems, I need to basically have a generative model, like a random graph that has this kind of planted community structure. And this is the most famous one by all means is the stochastic block model, where essentially you first sample latent variables that are binary, that would tell you the community of each node, and conditioned on these latent variables, you draw an edge with different probability depending on whether the two labels are the same or not. And depending on how different are these probabilities, I can make the problem harder or easier. Okay, so this is basically the signal-to-noise ratio, captures how hard is the problem by basically measuring how different are these probabilities. And so there are two ways maybe to think about this problem. One is basically trying to leverage ideas from basically like a variational method, right? So I basically try to identify the solution that I want as something that minimizes a quadratic form, right? And basically some notion of maybe the conductance of the graph, or some basically like a normalized conductance, etc. And of course, because the minimization is over a space that is discrete and very complicated to optimize, this gave rise to a lot of very beautiful methods that basically relax this search space. So you make the search space larger. For example, the ball of unit vectors, and that leads to spectral methods, or you can relax it to, let's say, a semi-definite program using like semi-definite programming. And there's another way to think about it is in terms of basically doing posterior inference in a graphical model, right? So I told you that there's a generative model, so you can basically try to infer the labels given the observed graph by basically trying to approximate the posterior distribution. As you know, the posterior distribution in general is intractable, so there's algorithms to approximate it. The most prevalent one is the belief propagation. Yes?
How do you measure performance?
It's measured by overlap. So basically, if you give me an estimate, like a binary vector that is your estimated class of labels, then I will take the dot product with the true one. I will remove the sign because I don't care about the level of the community, and then I will basically look at the fraction. And so what is interesting is that now there's a lot of research. As I said, Florent and Lenka are very important actors in this line of research that basically tell us, we have a very precise understanding on when is this problem statistically feasible, right? So for which values of the signal-to-noise ratio I can solve the problem, and for which values of the signal-to-noise ratio these algorithms are going to work well or not. So the question here that we ask is, maybe there are regimes in which these two thresholds are not the same, right? There's a gap. So the question is, well, there might be an algorithm that works well in this regime. There might not be an algorithm that works well in this regime. Can we use these models to maybe address or to get some insight about this question? So one way to relate these recovery algorithms with what I've described before is to get inspiration from these spectral methods. Okay, and so one way when one can think about these algorithms that work well is that if you give me a certain cost on the graph, you can measure it with an operator. Okay, and so you can characterize the solution as basically taking the sign of a very specific eigenvector of this operator. Okay, in particular, in the case of two community case, you can just look at the eigenvector corresponding to the second smallest eigenvalue. Okay, and so how would an algorithm produce this estimator? So basically, it needs to diagonalize an operator, so it needs to maybe run the power iteration algorithm, right? So a power iteration algorithm, if you unroll it, is just iterating over a very specific operator on the graph, right? And maybe just iterating on this operator and maybe adding some bias. So of course, this operator might not be known, right? So the idea that we have here in this work is, of course, to parameterize this operator because we don't know it. Maybe we can search for it by learning the operator, right? By basically learning the parameters over a certain polynomial of these operators. And so this is trained. So this defines a GNN. You train it with backpropagation, just a standard supervised learning problem. And what you see here in the case that you have two communities is that basically the two curves kind of overlap, right? So the BP is basically the one that is known to be optimum in this regime. And what you see here is that you wouldn't see it, is that basically the two lines here kind of overlap, okay? And so what you see here is that basically the model, basically learns how to solve this problem. And in a sense, it's actually interesting that even the linear model works well. Okay, so when I say linear model, it's the same model I described before, but you have no activation function. Just you learn the coefficients of these polynomials, and this actually, if you think about this power iteration, it's a linear model, right? You don't need to introduce like threshold or values, etc. Right? You just iterate on this operator and you project. But this is basically a setup where, in a sense, you could argue, why do you do that, right? You already know that belief propagation here is optimum, right? So, okay, it's good that you managed to learn it from the data, but can you basically take these ideas in a regime that is kind of harder, right? Where there's basically a gap between the polynomial methods and the statistical detection. And so for this, I just need one slide on belief propagation. I don't know how familiar the audience is with belief propagation, but the idea is that basically this algorithm, instead of basically iterating over an operator, you can think about it that it's basically going to send messages from and through the nodes, right? And so the way the messages are sent, are constructed, they're constructed in a way that exploits the adjacency not of the nodes but of the edges themselves, right? So basically, you can define neighbors, okay, that are basically respecting the sense in which the information is flowing, right? So every edge now becomes basically two edges, one that is basically pointing that direction and one that points that direction. And this is actually a construct that you can relate this to an operator on a graph that is called the non-backtracking operator, and we'll define it just in one slide. Okay? So the question that we ask here is that maybe we can leverage this information, right? So our model that I described before, it was only defined on operators on the initial graph, right? It was just using the adjacency and it was using the Laplacian maybe. So what we are going to do here now is basically try to upgrade our model, right? So instead of just having a model that lives on the original graph, there's nothing that prevents us from using basically, if I can map this graph to a new graph, where now, for example, the nodes of the new graph correspond to the edges of the original graph, I can define a new adjacency on this new graph that might provide information that is not readily available in the original, basically, node adjacency. And this is something that we use. So the adjacency in this new graph is what we call the non-backtracking operator, right? Basically, you can think about it's going to tell me that this edge and this edge are neighbors if basically I can send information that respects the sense, the flow information. And this is actually one way to upgrade the model that is also related, and so it's not exactly the same one, but there's other authors that are also thinking in these terms, right? Making the models more expressive. And there's a very beautiful work by Richie Condor in Chicago that uses tensors instead of these graph hierarchies. Anyway, so this model that basically is using now the line graph with this non-backtracking operator, now we can train it in the regime where we know that basically this problem is hard. There's a gap between what the maximum likelihood can detect and what belief propagation is basically shown to perform. And so what we saw here is that in this regime, so basically it's somewhere here in the middle, right? So this is the regime where BP works well, and this is the regime where maximum likelihood starts to fail. So what we show here is that, at least in our experiments, our model has an overlap that is significantly better than belief propagation. But there's a very big caveat here, right? And actually, this is something that, with Lenka we discussed, is that, of course, this is a result that is non-asymptotic, right? So basically, this is trained with a certain number of nodes, right? And many of the problems, many of the thresholds that are defined in the literature, they relate to behavior that is what happens as the number of nodes gets larger and larger and larger. What happens when n goes to infinity? So obviously, this is just an indication that there might be something, but it's far from being anything formal, right? But in a sense, it's interesting because what I said that is even the linear model, it's shown to basically, at least in this number of nodes, so this I think it's with 800 nodes, this is something that shows some promising numbers with respect to BP. There's another, so of course you can apply this on not just synthetic examples using random graphs. You can use it with, if you give me a data set of graphs that have, let's say, a ground truth community structure, it doesn't need to be ground truth. Just the user says that he wants to detect certain property of the graph, and we can call these communities. And then if I build a model that tries to predict this, what we show is that basically exploiting this information that lives on the edges is basically always showing us important improvements with respect to the baseline. And there's another example where we showed these results to work pretty good, is in random graph models that, so I'm not going to go into the details, but that they don't locally look like trees. Okay, so the reason why belief propagation is a good approximation to the posterior distribution is because in the stochastic block model, if you look at the graph, it looks like a tree. So it has like a very hyperbolic geometry. But there's random graph models that, in a sense, are meant to make belief propagation work not as good. And so here, our model seems to, at least, again, this is, of course, a non-asymptotic result. They seem to provide interesting gains in this kind of regimes. Yes? Oh, yeah, so sorry. So this is an overlap between 0 and 100. So it's basically, it's percent. Yeah. Sorry. Okay? And yeah, so this is, again, I'm not going to go into details, but you can think about this as a signal-to-noise ratio. Okay, so there's a, yeah. Okay, so what I said is that, motivated by this question of, okay, what is the take-home message here? What is the conclusion? So in particular, because the models that are linear are already performing interesting, in a sense, this motivated the question of maybe we can try to relate the two questions, right? So can we relate the question of how hard it is to actually solve a task, like to find an algorithm, to how hard it is to construct an algorithm that solves a task, to how hard it is to learn the algorithm, right? So in our problem, what the learning does is just searching in the space of parameters, right? It's not searching over the space of basically instances of the problem. And so can we relate these two questions? And so and of course, because we want to do some analysis, we have to start with something that is, that is not too hard. So we start with basically the linear model, which is actually not completely a stupid model, because as I showed, it already performs reasonably well. And so in that case, we can just basically write our solution, our estimator, as basically some, like a kind of a fancy power iteration that is parameterized by this vector of parameters, right? And this vector of parameters basically collects the coefficients of our polynomial. What is interesting here is that, okay, so next slide, sorry, is that this is our estimator, and basically what we have is that given this estimator, we can define our loss, and what it turns out is that this loss, you can express it as, as something that can be analyzed reasonably well. And so what is interesting here is that basically you can think of this as a polynomial, but the thing that makes it very different from the power iteration is that the operators that are involved in this polynomial, they don't commute, right? So if you want to understand the behavior of this estimator, it's not enough to just study the spectral properties of a given operator, right? There's like an algebra of operators that you need to understand. But anyhow, the resulting loss looks like basically an average of ratios. Okay, so if the expectation was basically inside the x and y, what this looks like a quadratic form over a sphere. Okay, so a quadratic form over the sphere, if you look at the landscape and you think for a second, is a landscape that has no pure local minima, right? Because basically, essentially corresponds to finding the eigenvectors of basically the generalized eigenvalue problem, right? So basically, if I could, in a sense, put the expectation inside, I would be very happy, right? There would be no problem in the landscape. So what happens here, essentially, is that we have this stability with respect to this concentration, in the sense that when can I almost do that? Well, I can almost do that if this random matrix concentrates, right? So as a function of the size of the graph, basically, if this quantity concentrates, in a sense, I'm allowed to swap. That's what is behind this, the proof of the theorem. I'm allowed to swap, basically, I'm allowed to put the expectation here. And what we can show is basically that there's this very nice property that the local minimum of this loss are controlled. So basically, they cannot be at arbitrarily long distance from the global minimum. So the gap between what the descent algorithm could achieve and the global solution is controlled by how, basically, the concentration of this quantity. And so this, in a sense, is opening some interesting direction where we can maybe relate, basically, how hard it is to learn these problems to how, basically, understanding the concentration of these quantities.
So
Yes?
If I follow correctly, you're going to have saddle points are all the non-top eigenvectors of this.
Yes.
No?
Yes.
So is that going to affect your ability to do these operations like the given that you're going to have
so, yeah, so in the informal thing, there's an assumption that basically says that it's easy to control that the saddles are strict, right? So if the saddles are strict, and this is something that is very easy to verify, so that we have basically the numerical verification that the hypothesis is correct, then basically you show that even if you add noise, basically if you so you can think this in terms of mean field, right? So basically this function is a perturbation of a function that has the strict saddle condition. And so you basically, by plugging the analytic assumptions, you show that if you perturb the noise in the way that this model perturbs the mean field, then it does not affect, it cannot change the index of the saddle points too much, okay? Okay, so I have like 5 minutes, I think. Okay, so I want to talk about another work that actually Alex Novak here, sitting in front, is one of the main authors, together with Solida Villar, that again is looking at the same methodology, like the same tool, on a different inverse problem. Okay, and this is an inverse problem that tries to basically match two graphs. Okay, so basically I have two graphs that can model, let's say, a network of factories and maybe a network of locations. And what I want to do is I want to find an assignment between factories and locations as to minimize some kind of metric distortion. Okay, so this is a very famous problem. It's called the quadratic assignment. It contains, of course, it's like a NP-hard. It contains the traveling salesman problem as an instance. And this problem is typically studied using either like a relaxation using like a spectral approach or semi-definite programs. And so I'm not going to go a lot on the details, but the way Alex set up the problem is, can we actually map the quadratic assignment problem to a linear assignment problem using a graph neural network? Essentially, we'll take the two graphs, and it will use like a Siamese architecture that will transform, that basically construct an embedding of every node, and then solve a linear assignment problem that is something that can be solved easily, like in a tractable way. And what we show here is that, again, by training it with these planted solutions, we are able to recover essentially the same performance as SDP in the Erdos-Renyi, but of course, our model is quadratic and SDP is quartic. And even in problems that are, in a sense, harder to match, like random regular graphs, what we show is basically like a clear improvement based on this like initial relaxation. So of course, we still don't understand very well why these things work. So this is something that is still interesting for us. And we are also interested in how can we apply this problem. So basically, quadratic assignment is a problem that is surprisingly useful in applications, right? So for example, in shape correspondence in graphics, this is very important, right, to align the two shapes. Or even now there's this very nice line of work in machine translation that tries to solve machine translation without supervision, right, by just looking at two languages and basically trying to align the two languages. So one interesting thing is here, can we use these techniques of quadratic assignment to map the two languages? Crazy idea, but who knows? And then I will just going to finish with a piece of work that we are currently working on. So here there are no results, but it's just try to show you that you can leverage these ideas beyond basically random graphs, right? And so here is actually a conjecture from harmonic analysis that is called the ZAUNER'S conjecture. I don't know if someone is familiar with it. So what is this conjecture about? So basically a frame, you can think about the frame as a set of collection of vectors, here like unit norm vectors in the d-dimensional complex space. And a frame is essentially like a fancy, it's like a generalized version of a basis, right? It is a way where you can actually do analysis and synthesis, etc. And so in particular, a frame is equiangular if basically all the dot products, like the angles between the vectors, are all basically they are all equally spaced in the, they are all equally spaced in the space, right? In a sense, the dot products are always the same. And so you can use, using like these fancy like Welch bounds, you can show that there's only the number of directions in the d-dimensional space that you can put that satisfy this property. You cannot go beyond d squared. And in that case, basically the correlation has to be precisely this one. And so the question here is, how can we construct these frames? And we want to construct these frames in a way that is very structured. Okay, so here's the one possible way to construct these frames. So I give you a vector, like just one vector, and now I'm going to define the action of a group. And in that space, there's actually a group that is called the Heisenberg group, that basically what it does, you can translate the vector. So basically you can shift the coordinates, right, using modular arithmetic, or you can shift the frequencies, okay, by using the modulation. This is the same thing, right? So basically if you give me one vector, I can construct d squared copies of this vector by translating it and modulating it. And the question that basically is the conjecture of Zauner is, for every dimension, can I construct a equiangular frame using this construction? So can I find this vector in such a way that when I construct these copies, I transform it into a frame that is equiangular? And this is actually important in quantum mechanics. So the existence of these things is important, and this is basically the symmetric information complete positive operator value measure. So this is like a very important thing in quantum mechanics. And there's actually a very nice research program trying to solve this conjecture for different values of d. And this is this funny thing that, it's proof for 17, 19, 27, 54, using a different mix of like algebraic geometry and numerical methods, right? There's a lot of supercomputers going into this, proving this thing. So one of the things that we are working actually with Thomas Stromer from UC Davis is to actually recast this problem as an inverse problem, right? As a phase recovery problem. Why? Because basically if I have a constraint on the dot products of these vectors, basically what I have, and I remove the phase, right? I have a constraint that basically, so the only thing I impose is basically that I have a vector and I apply this translation modulation and I apply a different translation modulation. This is very easy to show, right? That you can express this as basically a phaseless measurements on basically the outer product of X, right? So this is again using this like known tricks in the like facelift and phase cut related algorithms. But the problem is that in that case, the measurements that I have here are superstructured, right? So basically they are really generated by this Heisenberg group, right? So the classical algorithms of phase recovery, they rely on this kind of incoherence in the measurements, right? And so in this case, this strategy kind of doesn't have the right algorithm. So the question is, okay, how can we leverage this structure, right? There's a lot of geometry here in these measurements. So what we are basically proposing and doing as we speak, basically is learning the inverse problem. Okay, so again, this is a problem where it's very easy to construct the data set, right? You just construct X at random. If you give me X, I can construct this. I can construct the measurement, so I'm done, right? I can learn basically the forward pass, and the model is going to I can construct the forward pass, and then I'm going to learn the inverse. And so, and one of the things that we want precisely is a model that is not married to a specific dimension of the problem, right? So if we train the model and d equals 20, we don't want to have to retrain a new model for d equals 21, 22, right? So we want a model that is intrinsic, right? That basically only cares about basically the similarities between the measurements, right? And in that case, what we have described here during the talk is that these models that are living on these graphs are basically able to do that. In that case, it's like it's a GNN that is defined on this Heisenberg group. And so I wish I could show you some results, but I mean, Luca still running the experiment. So just to tell you that this is that this kind of story, you can actually extend it to problems where every time you have an inverse problem where the measurements or the data has some kind of relational structure that you can leverage, this is a good vocabulary to do that. And so with that, I'm just going to wrap it up. So just there's still many things that we don't really understand. So for example, how can we actually understand what properties these intermediate representations in these models are, how do they behave? How can we actually maybe use diffusion metrics, something a bit more general than diffusion metrics in some problems? And of course, the bane of our problem, of course, is how can we leverage these kind of non-asymptotic properties of these models to study things that are basically related to the problems of hardness in asymptotic hardness. And of course, there are many applications that we are thinking about. Again, in the case of basically computational hardness and algorithms, there's many problems. I mean, Alex was telling me about this noisy sorting problem, which is a nice problem where there's a gap. So every time there's a problem where there's a gap between the computational and the statistical, we are interested. So if you have a problem, just come to us, and we'll try to learn it. And then there's of course, a lot of interest in biostatistics, computational biology, so protein folding, like for example, generative models on graphs. That's another thing that is related and very interesting. And so with that, I think I will just thank you all and open for questions. And yeah, thank you.
So you, sorry, you mentioned that the diffusion distance is somehow stronger than Gromov-Hausdorff's. So you mean like Gromov-Hausdorff's convergence implies diffusion distance convergence?
Yes.
Like the topology is stronger?
Yeah, so the topology is a bit stronger, yes.
And is there a reason to think that this topology is better in terms of modeling the data? Like
no,
the data
so
would be...
I believe that Gromov-Hausdorff would be better. It's just that the proof, you know, I mean, I know how to prove things using this because it's just, you know, you just have like a norm on the operator. I still believe that Gromov-Hausdorff, I mean, many of the models are stable also with Gromov-Hausdorff, but this is an interesting direction to pursue. Yes,
right.
Good point.
I had a question about your particle physics example.
Yes.
Where does the graph come in there? I thought that in Atlas they just have images on the input.
No,
no.
So that's a good point. So in the particle physics, what you have is really like a point cloud. It's a point cloud that in that case lives in dimension 4, I think. And in that case, lives in dimension, I think. So every measurement that they have on the basically, so in this detector, you have basically information about the location, the physical location of the measurement, and you have information about, I think, the momentum, the angle, and maybe some intensity of the particle. So you construct this kind of low-dimensional, basically you have a signature for every measurement, and then you learn the graph. So when I say learn the graph, is that you construct an adjacency matrix that has some free parameters. And then because you're in a supervised classification problem, you backprop through the parameters of the kernel.
Okay, because I saw some papers where they were simply taking this as an image and applying CNN.
Then they quantify. So basically what the alternative is to say, okay, this basically is a sparse function. Like here it would be like in 3D, right, in a cube. And here it would be like a very sparse function in the cylinder. But if you do that, you basically first you need to the computational efficiency is lost because you are not anymore dependent on basically you lose the you have to quantify information. So you have to use quantification bins. So this can lose resolution, and then it becomes computationally expensive just because you have lots of zeros. So this is a way where we can actually leverage like the intrinsic basically information on the data. And there's just one last comment, is that in these problems, there's like the physicists, they have their own family of kernels, right? So they have what they call these QCD-aware kernels. So when we train the models and we train with respect to the parameters of this kernel, we can come to them and they can interpret what we learn, right? They say, okay, I learned this alpha equals 3. So then they're very happy and we can discuss, etc. So that's one thing, yeah.
Yeah, maybe similar to the question of Gabriel. It's about, suppose you want, so in the graph representation, if you want to be robust to random addition or deletion of edges, so if you're in the binary case, unweighted graphs, is the representation robust to that? Yeah,
so if you can translate this like asymptotically, if you add or delete an edge, it's not going to change too much the diffusion distance, right? So if I have two particles and I want to compare, you know, basically the distribution after time t, if I have added or removed an edge in the middle, you know, if the addition is basically small with respect to the size of the graph, I would expect that you get stability with respect to this diffusion metric. But if you have a problem where you want to basically, I mean, I'm sure there are problems in which this thing does not work, right? So problems in which, for example, if you just change a little bit the input, the solution completely changes. These are problems where I think there's no free lunch, right? There's no way you can leverage this kind of stability prior to solve them.
Thanks for the talk. So we assume that the labels are a deterministic function of the geometry of the input. So, for example, for ImageNet, is this assumption realistic, and do we need this assumption?
So let me try to see if I understood the question. So what you say is that you have so here, what I described most of the time, these are problems with like a planted solution, right? So you say, I assume there's I'm promised, so someone promises me that there's a structure in this graph. Can you find it? And so the way we set up the problem is as a supervised learning problem. So we have labels that are generated. But then, of course, there's always this leap of faith that if you want to now apply the model to a data set that does not come from the underlying generative model, then there's a problem, then you lose, right? If the statistical model is not appropriate, you have to train it again. So that's what, for example, I don't know if that's the question, but for example, in this setup, right? Here, we didn't use the SVM at all, right? For this model, we just used the labels that came from this data set.
So actually, the number of layers of the GNN should increase with the size of the graph, right? Like logarithmically, normally.
Yeah.
So maybe that's it. This is one of the reasons that. So in the case of that, you're learning the inverse problem, that it does not generalize well. So when you're trying to learn, like for instance, belief propagation, actually the algorithm is like doing the same thing
Yes.
across iterations.
Yes.
And if you fix the number of layers with respect to the size of the graph,
Yes.
maybe the question is, have you tried to maybe regularize the GNN by tying the weights around the layers?
So we have started to play with this model where instead of like, so there's two extremes, right? Either you can share completely the parameters of every layer, or you can unshare them, like make them free completely. So there's something in the middle that you can parameterize with a smooth function that basically says I have like a trust region, right? Where the weights at at layer k plus 1 have to be close to the weights at layer k. And then this is like you can basically extrapolate the weights. And this is related to this like neural architecture research, I think, from Brain that are using very similar ideas. Nothing conclusive so far. Yeah.
Right, it's probably a good moment to stop. So let's thank our speaker again.